Hello, and in this video I'm going to attempt to provide the follow-up that I promised to the simple main effects analysis video. Now, if you haven't watched that video, please watch it, because if you haven't, you're not going to understand the context of the example, because this is a direct follow-on. So let's go ahead and look at the example. We've got, again, essentially essentially the same data that we had before. It's been modified slightly, so the p-value is slightly different, but essentially the same data we saw last time, that for the weight in this condition there's no significant differences. It doesn't matter whether you're on the active drug or the placebo drug, no significant difference. But if you're in the therapy group, there's suddenly a very significant difference between whether you have the drug or whether you don't have the drug. One thing we didn't talk about last time was how to report the results of this, and that's in this table that we pretty much ignored this time. Last time, so we might say, for example, simple effects analysis showed that for those in the therapy condition, there was a significant difference between active drug and placebo. We'd report F, our degrees of freedom of 1 and 36, and F value and P less than 0.001 in this case. Now, the next thing I want to talk about is, I said in the last video that this isn't just splitting apart the interaction. It also gets benefit from the main effects. We use it as a test with the interaction, but it's not as clean as that. And the best way to demonstrate that is if we add up the sums of squares, or the amount of variability explained by both those contrasts. It equals approximately 119. And you'll notice, if we go up to our original ANOVA table, our interaction itself only explains about 82 units of variability. So where's the discrepancy? Well, because we were comparing both the SSRI groups at each level of therapy. We also have the sums of squares for the main effect as well. So if we said it was 119, but if we add 81 plus 37, we notice that is 119. So that's the first take-home point. We're not just split about the interaction. It's more complicated than that, because for whichever variable you're comparing both groups of, you end up adding in the sum squares appropriate to that variable. Another way to think about that is this interaction term has 1 degree of freedom, but if you look at the contrast, to do both contrasts, we've used up two degrees of freedom in the numerator. So that's just another way to visualize how there's more than just the interaction going on. The next thing we should look at is how a lot of people, when they use this technique, don't do it via the syntax like we did. They split the file and run 2 univariate ANOVAs. I think this technique is easier, but doing that will give us some interesting insights. So let's go ahead and do that. We have to remember what we split it based on, because you will get different answers depending on what you split it based on. So we want to split it based on whether an SSRI was prescribed or not, and then run 2 univariate ANOVAs effectively on therapy status. So let's go ahead and do that. We go up to data, split file, and split it based on compare groups based on the therapy status. This will give us two ANOVAs, one for the waiting-list people and one for the therapy people. So we hit OK, and now if we go to a one-way ANOVA, because we have to split on therapy status, we want to compare within therapy status groups the fact of prescription and medication. So we're just going to hit OK, and we've got both our contrasts. We get the same result. The therapy group was significant, and the waiting list group was not. But in terms of the actual numbers, we get slightly different numbers. Well, why is that? If I said a simple effects analysis is basically one way ANOVAs on each of the combination of the effects, well, is to do with this mean squared error. In a one-way ANOVA, because we're effectively doing two tests, we get two different error sums of squares. But in the simple effects analysis produced by SPSS, we use this pooled error term, and that's actually from the original model. We see error here, 6.671, and so that's the error term from the original model, and rather than being different like they are here, they are the same. What's the benefit of that? Well, it gives you more statistical power, and just to demonstrate, if for one of the contrasts we divide the between group sums of squares by the pooled error rate instead of its individual error rate. Let's see if we get the same results we do up here. So I'll do it for the therapy group, for example. So we want to divide 114.625 by, and instead of dividing it by 6.021 like it is in this one way ANOVA, we're going to divide it by the pooled error rate. And we notice we get 17.1, just like we do here, and that would yield the same p-value. Now, so that's the second take-home point, really. This simple effects analysis is just a series of one-way ANOVAs, but it uses a pooled error rate. Now, the first thing to do with that pooled error rate is the reason why we can just substitute that in and get more power is because our Levine's test was non-significant, so that's telling us statistically the variances are effectively the same, so we can afford to use that pooled error rate. But if the variances were different between the levels we were comparing, so in this case we split based on therapy status. If the variances were different based on therapy status, substituting in this pooled error rate would give us a bit of a murky picture. So that's a bit more on simple effect analysis. I know it was a bit disparate, but I hope you kind of understand more of the logic. And what I really want you to get from this video is that pitfall that when you do this, you're not just splitting apart the interaction, you're taking account of one of the sums squares for one of the main effects, which really, if we're just trying to split the interaction, we don't really want. It is possible to get significant simple effect with no interaction, so we don't really want that. But it's important to realise that if you do this, it's one way to do it, and I think it's probably the best way. But it's not without its shortcomings. So thank you for watching this video, guys, and I'll see you in the next one. Bye bye.